Hello, in this video we're in the multiple linear regression setting and we're going to introduce the principal components model. Now the first two pages are really notation and ideas for when we introduce the principal components model on page 3. So some of you can probably skip to page 3 and others would benefit from the first two pages. So let's jump in. We're going to assume that our design matrix is centered and scaled, and previous video 39 is a good reference for that. And here's our model where we've taken out the column of ones and separated it out. X is n by p and it has full column rank. Now in a centered model, the estimate of this is y bar. So we're going to subtract that to the other side, right? And just call this y star. And then this comes down. From previous video 56 on the canonical form, we multiply in between x and beta v prime, which is the identity matrix, right? So it doesn't change the model. But v are the can be thought of as v1, v2 to vp in columns, where v is p by p and the vi are orthonormal eigenvectors of x transpose x. And again, previous video 56 for more details. Now this here, so the epsilon comes down, v prime beta, we're just going to call gamma, and then we're going to write out v what it is into the p columns. Then we're going to multiply x into this, and then we get p columns. So xv1, xv2, all the way to xvp. And so in a sense, this is very similar to this model. Here we have p columns and a p by 1 vector, a parameter. And here we have p columns and a p by 1 parameter, vector of parameters. Now these columns here, we're going to split into the first R and the last P minus R. And we're going to call them ZR, and the R stands for the first R vectors, and C0 is the last. And the 0 is going to represent all these other columns have length that's very close to 0, and that'll make more sense in a second. Gamma, epsilon, and again, ZR is the first R columns, and C0 is the last P minus R. Now we're assuming that we have multicollinearity in our design matrix, and that means x is epsilon ill-defined. And from previous video 57, we know that there's eigenvalues, let's say the first R, that are greater than epsilon, and the last P minus R are less than epsilon, and the lambda I are the eigenvalues of x transpose x. And they're associated with the eigenvectors. So these eigenvectors, so V1 is associated with lambda 1 and so forth. Now in PV57 we showed that these first R columns, that none of these are epsilon ill-defined, and they form an orthogonal basis, which is a subset of the original column space of X. So none of these vectors and anything spanned by these vectors are not ill-defined. And then we notice that the last P minus R vectors are all ill-defined. But they also create an orthonormal basis for a subspace of the column space of X. But every vector spanned by these is epsilon ill-defined. So they're all very small in length, and they don't contribute much information to the design matrix. So we also showed that all these vectors, these plus these, creates an orthogonal basis for the column space of X. And we showed that the column space of X is actually equal to the span of both of these columns, or these span of both of these orthogonal bases. These are also perpendicular. So notes that note 1, vectors in 2 have all small length. So the most essential part of the column space of X is contained in the column space of ZR. Now the columns of ZR were orthogonal and carry unique information. That's kind of neat there. So the inner product of any two vectors is 0, and statistically we say they're independent or they carry unique information. Now note number 2, in previous video 56, we created a U matrix, and we split it into U1 and U2, and they're the n eigenvectors of x transpose. So this is an n by n matrix, and then this first one contains, so U1 contains the p eigenvectors associated with the positive eigenvalues lambda 1 through lambda p. And then these are eigenvectors, the rest of the eigenvectors in a sense, that are actually associated with the eigenvalue 0. Now we let the matrix L be all the eigenvalues. Well, not 0, but lambda 1, lambda 2 to lambda p. It's a diagonal matrix. So now we subset U1. Now remember, U1 is n by p. So we subset it into UR and U0. And so these are the first R columns, and actually they're associated with the R columns from page 1, and U0 and 0 is associated with the last P minus R columns, and 0 stands because those are associated with vectors that are really small in length. UR is associated with the eigenvalues lambda 1 through lambda R. Now in previous video 56, we derived the least squares estimates for the gamma parameters, but I didn't show it was unbiased, and so that's what I want to kind of make up for that in this video. So the expected value of the least squares estimate of gamma is this. So in PV56 we showed that the least squares estimate is L to the minus 1/2, and so raised to the minus 1/2, it says that these are to the minus 1/2. So it's 1 over the square root of lambda 1, 1 over the square root of lambda 2. That's what this represents. U1, of course, is here, and Y. But when we take the expected value, these are constant, so it goes in here. Now the expected value of Y is x beta. But we're going to write x in its singular value decomposition form and beta here. So now this product is 0, or the identity matrix, and this product is the identity matrix. We're left with V prime B. But that's what we called gamma, so it is unbiased. Now from previous video 42, the average squared length of this vector of least squares estimate of beta minus the actual parameter beta, we showed it was this. So it's the sum of the variances of the least squares estimates, and it was sigma squared, the sum from 1 to p of 1 over lambda I. So if there's multicollinearity, some of these eigenvalues are really small, and 1 over a small number is actually big. It's quite large. So when we have multicollinearity, it inflates the variances associated with these least squares estimates. Now in previous video 56, we showed that the mean squared length of this vector, so least squares estimate of gamma minus the parameters itself, was equal to the sum, also the sum of these variances, and it turned out to be the same. And so whatever model we use, the sum of the variances of our least squares estimates are equal. But the unique thing here is the columns in the canonical form that we're using here, they're all independent, they're orthogonal. So we're going to be able to separate this associated with whatever vector we use. Now there's a property that says that since the columns are orthogonal, we only need the ith column, is needed for the least squares estimate for gamma I. So to me, and that's kind of crazy, we didn't prove it, and I may in a later video, So to come up with the least squares estimate for the ith parameter, the ith gamma parameter, we only need the ith column, and that's kind of crazy. So previous video 56. Now the ith column in our model is XVI. So it's XVI prime XVI. So it's kind of like X prime X inverse X prime, or transpose Y. So this is the least squares estimate, and we can do that because all the columns are orthogonal. And to me, that's kind of cool in itself. So now we just unpack it. So we transpose that, and we get this inverse is staying. Transpose that. Now this is an eigenvector associated with X transpose X. So then we get the eigenvalue eigenvector combination. And so the eigenvalue comes out front, and VI transpose VI is 1. So we're left with the eigenvalue inverse, and that's what this is. So over here we get VI, and then X, we write it in the singular value decomposition form, transposed, and then we have Y. Now, here U1 prime Y, we've called it Y star. And actually this Y star now, I wish I wouldn't have done it on page 1. This is different than the original Y star. And then we have L to the 1/2, and here we have VI. And when VI is multiplied by each column, since they're orthonormal, it's all 0 until we get to the ith column. And that's what this represents. And then we have lambda I inverse. Then, so when we take this vector times this diagonal matrix, it's all going to be 0 until we pick off that the ith lambda, so it's going to be square root of lambda I. But then when we factor that out, then that reduces to lambda I, the square root of the minus 1/2. And then we take this and multiply it times this y vector, and we just pick off the ith component of yi star. Well, this is what we have called, that's the least squares estimate for yi hat. And if you look at in my previous video 56, that's exactly what we derived using the whole model. But since they're orthogonal, we only need the ith column. And that, anyway, I like that property. So now the variance of our least squares estimate, we are going to use this one right here, but we're going to unpack yi star to be u1 prime y. So that's what this is here. We've multiplied that in to get this. Then it's the variance of y. Then we have to transpose that out back. And then the variance of y is sigma squared I. So the sigma squared come out front, the identity matrix. Then u1 prime, u is the identity matrix. And this row vector times this column vector, it's, these are multiplied, so you get lambda I to the 1 minus 1. And we're adding up a bunch of zeros. And we have the sigma squared out front, and then we get this. So this is the variance. And so why is this important? Now, and this is what I was saying earlier, the variance of gamma I hat is just this. So this sum, they're actually independent. So the variance of gamma 1 hat is actually sigma lambda 1 inverse, right? So each column is kind of associated with each, well, it's not kind of, it is associated with each one of these. So maybe if we eliminated the columns that had a really small eigenvalue associated with it, and get rid of them, then this sum of the variances decreases substantially. And actually that's part of the idea of principal components. Notes 1, the effect of an ill-defined design matrix affects both of these sums equally. The columns of the, remember these are the ill-conditioned columns associated with the lambda values that are really small, say less than epsilon. They substantially increase this mean squared length here. So now the idea in principal components is this. So the general development is that we drop the P minus R epsilon ill-defined vectors, Z0, right? So this is the model in canonical form, and Z we split, and then the gamma vector will have to split, right? So this is essentially that, but it can also be think of as this plus this. Well, these are these ill-defined vectors, so they're really, really small. So this contributes very little to the overall model. So why don't we just drop it, right? And that's what we do. So what's left over is called the principal components model. And this is it. We're only keeping the well-defined columns, or the ones that are not epsilon ill-defined. So now the least squares estimate for gamma R is, well, we need some notation first. L, remember, was a diagonal matrix of the eigenvalues, but we're going to let LR be the first R eigenvalues and L0 be the last P minus R. And V, which is the eigen vectors associated with X transpose X, associated with these. But we're going to let we're going to split it into VR and V0 like this. So note that VR or ZR is actually XV1 all the way to XVR, and we can unpack that into just call it XVR. This is the same as this. Now let's find the least squares estimate. So the least squares estimate, remember, it's X transpose X inverse X transpose Y, and that's what we do here. So this is like the new X, Okay. But now let's write what ZR is. It's this. Unpack it. Now let's transpose that in, and we get this. This is transposed. But these are eigenvectors to X transpose X. So then we get the eigenvector times the eigenvalues. Well, this right here is the identity they're orthonormal, so it's the identity matrix. And then here is VR, but we write out the singular value decomposition for X, which is this, and we get Y. So now let's unfold this. So here we get LR inverse, which is this, and here we get VR. Remember, V is VR and V0, so that we get the identity and then 0 because they're orthonormal eigenvectors. We get 1/2 U1 Y. So now to go here, so this multiplied by U1, oh, I skipped a step. So this multiplied by L to the 1/2, it picks off the first R component. So that's LR to the 1/2. And then everything else stays the same. Here, so if we left factor out a LR to the 1/2, then that makes that a LR to the minus 1/2. Then we multiply the identity matrix times, in 0 times U1. We're only picking off the R columns. So that's what this is. So this is the least squares estimate of the principal components model. Now the expected value of this is this, okay? So we have LR to the 1/2 UR, and then the expected value of Y is X beta, but we write the specular value decomposition of it in beta. Now we have LR and UR and U1. Remember, U1 is UR and U0, so we get the identity matrix and 0. We have L to 1/2, and V prime V we just write as gamma. This multiplied here, it picks off the first R, and that's why it's LR to the 1/2. Then, right, so then when we multiply this into both of those, we get the identity and 0. and then this is going to pick off the first R component, so it's gamma of R, so it's, which says it's unbiased. Now the variance of gamma R hat, and so our least squares estimate was this. So the constants come out front times the variance, and then those constants are transposed out back. The variance of this is sigma squared I, so the sigma squared comes out front in the identity matrix, and then this times this is identity, and then this times this, you get LR to the minus 1/2, which is a diagonal matrix of the 1 over the eigenvalue. So we get sigma squared this diagonal matrix. So that says, all the off diagonals are 0. So all these least squares estimates of the gamma are independent. That's a big part of when we're testing in the model. So now to estimate the original beta from the principal components model, remember that's usually what we're interested in, is those how to interpret the beta parameters from the original model. And we've removed the ill-conditioned vectors from our design matrix. And so what does that do to our original estimate, and how do we get it back? Now in the canonical form, when we're not removing the ill-conditioned vectors, we just multiply V to our gamma, and then that reduces to beta. But we've removed it, so we multiply VR times our least squares estimate, gamma R hat, and then that's called our principal components estimates for beta. So now let's look at the variance of the sum of all these components, which is this. Now these are individual variances, so it's the variance of component 1 plus the variance of component 2, variance of component 3. That's what this represents. But now if we kept it in vector form and took the variance, we create a variance covariance matrix. But if we just sum the diagonal elements, which is summing the variances, that's what this represents. So we just take the trace. But then the variance of this, remember that's VR, right? Now this variance, we take the constant out front and transpose it out back. That's what we get here. And then since it's the trace, we can move that, and VR prime VR is the identity matrix, so we're just, that's what I have here. So we're left with just the variance of this, which is sigma squared, and then that diagonal matrix. So it's the trace of that diagonal matrix, which are, it's the sum of the lambda I to the inverse. So it's it. Now, but notice that it only goes from 1 to R, not 1 to P. We've removed the P minus R eigenvalues that are really small. When you take 1 over a small number, it's large. So we have significantly reduced the total variance. But at what cost? We've removed vectors from our model. Well, the cost is now our principal components estimate is biased. We've reduced the variance significantly. But let's calculate the bias, and this is the last thing we're going to do in this video. So the mean of the principal components estimates is this. So the principal components estimate, so here we have VR, which is what that VR. Now the least squares estimate for gamma R was LR to the 1/2 UR prime Y. And so the expected value goes into that Y. Now the expected value of Y is X beta, but we're going to write X in its spectral decomposition form and then beta. So now we just unfold it. So these are the same, but UR, remember U1 is UR and U0. So the UR and UR is identity and the rest are 0. That's where this comes from. L to 1/2 V prime beta. So then this times this, it grabs the LR components, right? That's why we get this over here. Now, when we multiply this in, we get the identity matrix here in 0, right? And then this right here times the V, it's only going to grab the first R columns, so we get VR prime beta. Now let's look at a note here before we finish this. The identity matrix can be thought of as V prime, but V was really VR and V P minus R in the same way transpose. So then when you do this multiplication, you get this this matrix, the sum of these matrices. But if we take this to the other side, then we get an expression for VR that we can substitute in there. So we substitute it in, I minus VPR, VPR prime. And then we multiply the beta in, and we get this. So the expected value of the principal components estimates are biased, right? Yeah, and maybe we'll stop there because it's getting long, but I felt like I needed to introduce the notation and the ideas to really cover this in-depthly. Now, the big note that we're not going to cover is there's different ways to use and test this model. And you should read up more on this topic. It's pretty in-depth. There's different strategies, which vectors to use, how do you test the beta parameters to eliminate columns, or the gamma parameters. Well, anyway, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.